Hello everyone. In this video, we'll be covering concepts from the course of Chemistry 1412, also known as General Chemistry 2. I'm going to go ahead and share my screen so that you guys can see a PowerPoint presentation for the concepts that we'll be covering today. So the concept that we're covering today is going to be cells and batteries. The first cell is the electrochemical cells. There are two types of cells that fit this category, a voltaic cell and an electrolytic cell. A voltaic cell is a spontaneous redox reaction, and it is used to produce an electric current. So for a voltaic cell, the system is going to be doing work on the surroundings. For an electrolytic cell, an electric current is used to drive a non-spontaneous redox reaction. So this means that you have to have some form of electric current, such as a battery, to drive the reaction to occur. And for an electrolytic cell, the surrounding is going to do work on the system. Both types of cells are constructed using two electrodes placed in an electrolyte solution. The anode is the electrode at which oxidation will occur. We can remember this by NOx. So N is the anode, ox is the oxidation. The cathode is used when an electrode is in reduction. So we can remember red cat. So reduction and cathode. So you can see that what makes them different is the charge on the anode and cathode. So what we're used to is the anode being negative and the cathode being positive. We're going to see this in a voltaic cell. However, it's going to be the exact opposite for the electrolytic cell. So it's going to have a positive anode and a negative cathode. This is something important to know when you're taking an exam. Construction of a voltaic cell. Each half reaction takes place in its own half cell, so that the reactions are physically separated. And we'll be able to see this in the picture diagram on our next slide. Each half cell consists of an electrode and an electrolyte solution, as we stated before. The half cells are connected by an external circuit, and a salt bridge will complete the electrical circuit. So as we see, this black wire that goes from one of our metals to the other metal, this is going to be that external circuit. And we're going to see this on both the voltaic and electrolytic cell. The big little piece of U-shaped metal right here is going to be that salt bridge that we mentioned. And then we can also see that for a voltaic cell, the anode is negative, the cathode is positive. For the electrolytic, the anode is positive and the cathode is negative. But no matter what, we're going to notice that our anode is going to push the electrons to our cathode in both the voltaic and electrolytic cells. And so we're going to watch a video that is going to explain this just a little bit more in depth.
In the last video, we saw that if you took some solid zinc and stuck it in a solution of copper sulfate, that the zinc will essentially give electrons to the copper, so then you have zinc cations that are in the solution. So essentially it will become a solution of zinc sulfate, and the copper, once it gets those two electrons, is going to go into its neutral, its solid state, and it's going to precipitate out of the solution. And we saw the reaction right over here, solid zinc plus copper sulfate in solution in water. It's an aqueous solution. You have the copper, the solid copper precipitating out, and now it's a solution of zinc sulfate, that the zinc has essentially been oxidized. It lost two electrons. It went from neutral to positive, and the copper went from positive to neutral. So the copper took those two electrons. Zinc was oxidized by copper. It lost electrons to the copper. Copper was reduced by zinc. Its charge was reduced by zinc. It gained electrons from zinc. Now this by itself is interesting. It's an interesting redox reaction. Something was oxidized, something was reduced. But wouldn't it be interesting is if we could somehow somewhat separate these two half reactions and make these electrons travel over a wire. Now, why would that be interesting to make electrons travel over a wire? Well, if electrons traveling over a wire, that's a current, and you can make current do useful things like power a motor or a light or whatever it might be. And so essentially, if we can do that, we would have constructed something of a battery. If we can keep that going, if we can keep the current flowing, we would have constructed something like a battery. And what I have here, this is a picture of a galvanic, sometimes called a voltaic cell, and this is doing exactly that. It's separating these two half reactions and separating them with a wire. So zinc can give copper its electrons, but it forces the electrons to go along this wire and produce an actual current. So let's think about why this is working. So you have solid zinc right over here. We've already said that, look, the solid zinc wouldn't mind giving its electrons to copper. Copper wouldn't mind taking it. Copper is more electronegative. And so you have a reality where the solid zinc could give away its two electrons and become the cation zinc, so a positive charge, and then it dissolves in the water. Once it has a positive charge, it's easy to dissolve into a polar solvent like water. And then you have those two electrons. Where are those two electrons going to go? Those two electrons can then go and be given to the copper. And both zinc and copper are great conductors of electricity. They're transition metals. They have these seas of electrons, so electrons can travel within them fairly easily. And so you have your two electrons. So those are your two electrons that I showed traveling in green, and they can come all the way to the bottom of where this copper bar is in contact with the copper sulfate solution. And now you're going to have an atom, a cation, I should say, an ion of copper, that when it comes in contact with those electrons, it's going to nab them up. It's going to nab them up and become neutral. So it's going to nab them up and become neutral. And when it becomes neutral, it's going to precipitate out of the solution. It's going to precipitate onto that bar. Now, you might be saying, look, if more and more positive things, if more and more of this zinc, this positive zinc is flowing in this, wouldn't this make this an imbalance? And if this solution becomes too positive, then the electrons wouldn't want to leave as much anymore. So if you just have a bunch of, if this starts becoming very, 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 very positive, and similarly, if all of the positive stuff, if all of the copper cations are capturing the electrons, this solution is going to become more and more negative. It's going to have more sulfate and less of the positively charged copper ions. So what can we do to make sure that that doesn't happen too quickly? Well, what we do is we use something called a salt bridge. And this salt bridge right over here, salt bridge, this helps neutralize that effect that we just talked about. And with a salt bridge, you can kind of view it, it's not going to be liquid, because then everything inside of it would just fall out. You can kind of view it as a goo of a salt. In this diagram, we picked sodium sulfate as our salt. So for every sulfate molecule, you have sulfate anion, you have two sodium cations. And so what's going to naturally happen here? Well, as this becomes more and more positively charged, as more and more positive zinc ions go into the solution, the negative sulfate ions are going to want to come out of here. So the negative sulfate ions are going to want to leave all of their negative friends right over here, go into the salt bridge, and the ones that are already in the salt bridge are going to want to come out here. Similarly, the sodium right over here will be tempted to help neutralize. The sodium could go in this direction. Let me do it this way. Could go in this direction and help neutralize any net negativity that's happening there. And so that will keep each of these solutions from becoming too positive or too negative, and allow this current to continue to flow and do useful things.
All right. So hopefully that was able to explain the makeup of our voltaic cell. And now we're going to get into active and inactive electrodes. An active electrode is an active component in its half cell, and it is a reactant or product in the overall reaction. An inactive electrode provides a surface for the reaction and completes the circuit. It does not participate actively in the overall reaction. Inactive electrodes are necessary when none of the reaction components can be used as an electrode. And inactive electrodes are usually unreactive substances, such as graphite or platinum. Electrical potentials and the voltaic cell. When the switch is open and no reaction is occurring, each half cell is in equilibrium state. So as we can see right here, Zn is a stronger reducing agent than Cu. So the position of the Zn equilibrium lies further to the right. Zn has a higher electrical potential than Cu. When the switch is closed, the electron flow from Zn to Cu to equalize the difference in electrical potential. The spontaneous reaction occurs as a result of the different abilities of these metals to give up their electrons. And now we're going to talk about cell potential. A voltaic cell converts the delta G of a spontaneous redox reaction into kinetic energy of electrons. The cell potential, which is E cell, of a voltaic cell depends on the difference in the electrical potential between the two electrodes. Cell potential is also called the voltage of a cell, or the electromotive force, which is EMF. When a reaction is spontaneous, the cell potential is going to be greater than 0, which means that if it's a non-spontaneous process, your E cell will be less than 0. The standard electrode potential. The standard electrode potential, which is E0 half cell, is the potential of a given half reaction when all components are in their standard states. By convention, all standard electrode potentials refer to the half reaction written as a reduction. The standard cell potential depends on the difference between the abilities of the two electrodes to act as reducing agents. We can calculate our standard electrode potential by subtracting the E0 of the cathode, or the reduction, minus the E0 of the anode, or the oxidation. So let's do an example. The redox reaction of peroxydisulfate with iodine has been used for many years as part of the iodine-Fock reaction, which introduces students to kinetics. If E0 cell equals 1.587 volts and E0 of the cathode half cell is 0.536 volts, what is the E0 of the anode's half cell? So let's go ahead and move to our boogie board. So we know from our last slide that the E cell equals the E cathode minus the E anode. But we're not looking for E cell, we're actually given E cell. So we want to arrange it to where we have everything equal to the E anode. So we can say E naught of the anode equals E cathode minus E cell. And so all we would have to do is plug in the variables that they gave us. So we know that the E cathode is 0.536 volts minus the E cell, which was 1.587 volts, and this will give us CE anode. So our E anode equals negative 1.05 volts. Let me go ahead and re-expand this. So it's pretty simple as long as you know the equations to use and how to plug everything in. So let's do a second example. Calculate the E cell and indicate whether the overall reaction shown is spontaneous or non-spontaneous. So we have our two half reactions, and we have H2O2 plus 2H plus 2E minus produces 2H2O with an E naught of 1.77 volts. Our second half reaction is Fe3 plus E minus yields Fe2 plus, and its E naught equals 0.77 volts. We now have our overall reaction of 2 Fe3 plus 2 H2O yields H2O2 plus 2H plus 2 Fe2 plus. And then they give us our different options for an example, our answers. So let's go back to our boogie board. So we have H2O2 plus 2H plus 2E minus yields 2H2O, and its E naught equals 1.77. Our second half reaction was Fe3 plus E minus yields Fe2 plus. Its E naught was 0.77. So the first thing that we have to do is identify which one is the oxidation and which one is the reduction. So this one is going to be our anode because it's being oxidized. So we know that this is an ox. So it's an anode and it's oxidized. And we know that this one is our red cap because it's a reduction, which means it's our cathode. So we can set up our equation that we had before. So E cell equals E cathode minus E anode. So we're going to have E cell equals our cathode, which is 0.77, minus our anode, which is our oxidation, which is 1.77. So this is going to give us an E cell of negative 1.00 volts. So now we have our first part of our answer. So we know what our E cell is equal to. We now have to determine whether it's spontaneous or non-spontaneous. So we have to remember that E cell is greater than 0 if it's spontaneous, and E cell is less than 0 if it's non-spontaneous. So we have to look and see. We have a negative 1, which means our E cell is less than 0, which means our reaction has to be non-spontaneous. So our answer would be A, E cell equals negative 1.00 volts, and it's non-spontaneous. Let me expand it so that you can see a little better. And now we're going to move on to comparing each half cell values. Standard electrode potentials refer to the half reaction as a reduction. E0 values therefore reflect the ability of a reactant to act as an oxidizing agent. The more positive the E0 value, the more readily the reactant will act as an oxidizing agent or to be reduced. It will be the cathode. The more negative the E value, the more readily the product will act as the reducing agent or be oxidized. It will be the anode. And now we're going to get into more of our equations to use. So free energy and electrical work. For a spontaneous reaction, delta G is less than 0 and E cell is greater than 0. And we can use the equation of delta G equals negative NSE cell, where N is the number of electrons transferred, F is a constant, and it's going to be 9.65 times 10 to the 4 joules divided by volts times moles times electrons, and delta G is our Gibbs free energy. We understand, under standard conditions, delta G naught equals our equation that we stated before, or it can equal either the two below. So it can be E cell equals RT divided by NS ln of K, or it can be E cell equals 0.0592 volts divided by N times log K. We'll use this right equation when we have a temperature of 297.15 Kelvin. And now we're going to see the Nernst equation. So this is going to be for cell potential and concentration. So the Nernst equation is E cell equals E naught cell minus RT divided by NS ln of Q. Remember, Q goes back to what we learned earlier on in the semester, which is the concentration of your products divided by the concentration of your reactant. When your Q is less than 1, your reactants are greater than your products, ln of Q is greater than 0, so your E cell will be greater than your E naught cell. If your Q is equal to 1, your reactants will be equal to your products. So your ln of Q equals 0, and your E cell and E naught cell will be equal to each other. If your Q is greater than 1, your reactants will be less than your products. Your ln of Q will be greater than 0, and your E cell will be less than your E naught cell. If we have a temperature of 298.15 Kelvin, remember to use the following equation. So let's do an example. It says calculate the cell potential of a ZnCu cell when the concentration of Zn2+ equals 1 molar and the concentration of Cu2+ equals 1 molar at 25 degrees Celsius. And then we have our two half reactions where it says the E0 for the reduction is positive 0.34 and the E0 for the oxidation equals positive 0.76. And then they give us our overall reaction with an E cell of positive 1.1 volts. So we need to calculate the cell potential. So let's go to our boogie board. So we know that let's go ahead and write everything out. Cu2+ plus 2E minus yield Cu, and use a solid, and this is aqueous. And it's E naught, so the reduction, so it's our cathode. Because remember, reduction is red cat equals positive 0.34. And then our second half reaction is Vn solid yields Vn 2 plus, which is aqueous, plus 2E minus, and this was our oxidation, so it's our anode, equals positive 0.74. And for Cu, they told us our concentration for Cu 2 plus equals 1 molar, and that our concentration for Vn 2 plus is also equal to 1 molar. And then I'm going to go ahead and write a line for our overall reaction. So our overall was Cu 2 plus aqueous plus Vn solid yield solid copper plus Vn 2 plus aqueous with an overall cell potential or E cell of positive 1.10 volts. And this is going to be at 25 degrees Celsius. So we need to convert that degrees Celsius to Kelvin to see which equation to use. So 25 degrees Celsius is going to equal 298.15 Kelvin. So this should ring a bell. This tells us that we're going to use the equation E cell equals E naught cell minus 0.0592 volts divided by N times log of Q. So let's go ahead and plug some stuff in. So we know that N is the number of electrons, and we see that we have 2. So N is going to be equal to 2. So you'll plug a 2 right in here. We're given our E cell, or E naught cell, and then now we need to figure out what our Q is. So remember that Q is going to be when you're not dealing with pure solids. So we'll look at our overall reaction and cancel out our pure solids. And we're left with Vn2 plus and Cu2 plus. What we need to do is do our product, which would be our Vn2 plus, divided by our reactants, which is Cu2 plus. They told us our concentration, so it's 1 divided by 1. So 1 divided by 1 gives us 1. So our Q equals 1. So we have E cell equals 1.10 minus 0.0592 divided by 2 log of 1. So when we plug in log of 1, this is going to give us 0. So we have E cell equals 1.10 minus 0.0592 divided by 2 times 0. So we know that anything times 0 gives us 0. So we have E cell equals 1.10 minus 0, which means our E cell equals 1.10. What we notice is that our E cell and our E naught cell are equal to each other, which makes sense because when we said our Q equals 1, our E cell should equal our E naught cell. And that is information that we saw on one of our previous slides. So this makes sense that our E cell is 1.10 volts. Okay, let's go ahead and go back. And we'll move on to example 4. You'll notice that everything is pretty much the same except for the concentration of Zn2+. It went from 1 molar to 10 molar. So let's see how this will change things. So we have our Cu2+ aqueous plus 2E- yield solid copper, and Re, remember this is reduction, so it's a cathode, red cat, equals positive 0.34. We have our second half reaction, which is Zn solid yields Zn2+, which was aqueous, plus 2E-, and this is going to be our anode because it was our oxidation and ox, so it's our anode, and that's going to be positive 0.76. And then our concentration for Cu2+ is still 1 molar, while our Zn2+ is going to be 10 molar. And this is still at 25 degrees Celsius, which means we're still going to use that equation that we used in our previous example. So let me go ahead and write out our overall reaction of Cu2+ aqueous plus solid zinc yields solid copper plus Zn2+ aqueous, and this is going to give us an E naught cell of positive 1.10 volts. So let's write out our equation. So E cell equals E naught cell of minus 0.0592 volts divided by N times log of Q. So just like before, we look at our electrons. We have 2, so our N is 2, and we need to figure out what our Q is. So remember, we cancel out our solids and we do product. So 10 divided by 1 equals 10. So our Q is equal to 10. We plug 10 in here. We have E cell equals 1.10 minus 0.0592 divided by 2 times log of 10. So log 10 is going to give us 1. So we have E cell equals 1.10 minus 0.0592 divided by 2 times 1. So if we plug this in, we're going to get E cell equals 1.10 minus 0.03 times 1. When we multiply these two together, we get E cell, let me write it up here. So E cell is going to be equal to 1.07 volts. And let's go ahead and box this. So this is our answer. This is what our E cell is. And it makes sense because our Q is greater than 1, which means that our E cell should also our E naught cell should be greater than our E cell. So our E cell should be less than our E naught cell. And it is, because we have 1.07 as our E cell, which is less than our E naught cell of 1.10 volts. All right. So let's go ahead and go back to our PowerPoint presentation and start to cover electrochemical processes in batteries. A battery consists of a self-conducting voltaic cell arranged in series so that their individual voltages are added up. A primary battery cannot be recharged. So remember, primary cannot be recharged. The battery is dead or cannot be used anymore when the cell reaction has reached equilibrium. However, for a secondary battery, it can be recharged. So this is going to be something such as a car battery or like a cell phone battery. Once it has run down, electrical energy is supplied to reverse the cell reaction to form more reactants. Fuel cells. In a fuel cell, also called a flow cell, reactants enter the cell and products leave, generating electricity through the controlled combustion. Reaction rates are lowered in fuel cells than in other batteries. So an electrocatalyst is used to decrease the activation energy. So here's a knowledge check. Is a battery considered a primary or secondary battery? The answer, a car battery is a secondary battery, right? I should say battery, because it is rechargeable. So know the difference between a rechargeable and non-rechargeable battery. So rechargeable means it's secondary and non-rechargeable means it's primary. And corrosion and environmental voltaic cells. Corrosion is the process whereby metals are oxidized and their oxides and sulfides. The rust of iron is a common form of corrosion. Rust is not a direct product of the reaction between Fe, or iron, and O2, oxygen, but arises through a complex electrochemical process. Rusting requires moisture and occurs more quickly at lower pHs in ionic solutions and when the iron is in contact with a less active metal. Electrolytic cells. An electrolytic cell uses electrical energy to form external sources to drive a non-spontaneous redox reaction. So we have our anode, we have our cathode, and we have our E cell, and they also provided us with our delta G naught. As a voltaic cell, oxidation occurs at the anode, and reduction takes place at the cathode. An external source supplies the cathode with electrons, which is negative, and removes them from the anode, which is positive. Electrons flow from cathode to anode. So let's do a brief overview. We covered voltaic cells, which is a spontaneous redox reaction is used to produce an electric current. For an electrolytic cell, an electric current is used to drive a non-spontaneous reaction. We also had cell potential, which we used the Nernst equation, and we went over a couple examples of using it. We covered standard electrode potential, which we used the equation E naught cell equals E cathode minus E anode. And we also went through an example of that. And then finally, we covered batteries, which we covered primary, which is the non-rechargeable, and secondary, which is the rechargeable. So let me stop sharing my screen. So that is all that we have for today. I hope that this video was useful, And if you have more questions, feel free to email your professor. Thank you and have a good day.